Hey, welcome back. So this is the first real section of the course, and we're kicking it off with something really important, something big. It's called Big O notation. And when I say big, I don't mean that it's long or difficult even. It's big in significance. It's something that I had no choice but to start the course off with this topic because, at least if I wanted to make it a good course, because it's going to come up in, I won't say every single video, but maybe 70% of the videos in the rest of the course. Don't hold me to that, but a lot of videos, a significant number. We're going to refer back to what we talk about in this section. So before I even explain what it is, I have a quick warning. There's a bit of math in this section, and I'm warning you not to scare you away, but actually to encourage you to push through it if you do struggle with math, or if you're someone who hasn't heard the word logarithm ever or in 10 or 20 years. That's going to come up in this section at the end, but don't panic, because what we're going to do here in this section is establish a framework for talking about code in the rest of the course. And that does involve some math up front, but it means that the rest of the course isn't going to be, some of it will be mathy, definitely, but this is not indicative of what the rest of the course will look like. So just push through it. If you like math, great. If you have some problems with this section, just remember that the entire course isn't like this. And we're just getting it out of the way because, like I said, it has to come first. I don't really have a choice. Okay, sorry if I scared anybody there. Let's talk about the objectives for this section. So in this video, we're going to start by just talking about the need for something like Big O notation. I haven't even mentioned what it is, so we're going to get to that. Then we're going to describe what it is, so why we care about it, what it is. We're going to learn to simplify Big O expressions. We'll define time complexity and space complexity. We'll evaluate time complexity and space complexity of different algorithms using Big O notation. And then we'll describe what a logarithm is, a bit of math at the end there. So I know it's a lot, but we're going to start with this first bullet point. Motivate the need for something like Big O notation. So what is the idea here? Well, this course is about algorithms, it's about solving challenges, it's about computer science and data structures, but for every topic in this course, there's 10, 20 different implementations or solutions that could work, probably way more. How do we know what's best? So let's scale it down a bit just to a single problem. Let's say that there are two valid solutions to a problem. They both work, and they're different, not just in names or variable names or something, but totally different in approaches. One uses a loop, the other uses, a list or a string or something to accomplish the same task. How do we know which one is best? That's really what Big O is about. It's a system, it's a way of generalizing code and talking about it and comparing code and its performance to other pieces of code. Okay, so here's a more concrete example. Write a function that accepts a string input and returns a reversed copy. If I asked you to do this, which maybe some enterprising students will do this and come up with some creative solutions, off the top of my head, I can come up with 3-ish solutions, different approaches, and I'm sure there are way more out there. I actually found this post on Stack Overflow that has 10 different implementations in JavaScript, and they're all different. Like I said, it's not just a different variable name. It's not just switching a for loop for a while loop. There are different approaches. How do we know if all of these work? Here's one using a for loop and an array. Here's one that uses no loops and it's no arrays. It's all, actually, I guess there is an array in there at one point, but it's all built-in methods. How do we know which one's best? Well, we'll get there. But wouldn't it be nice if there was sort of a system for classifying code or for comparing it, which I've already spoiled it and said that's what Big O sort of is. Think of it sort of like if we're talking about earthquakes. If this was a seismology 101 class, very early on, I would start off by talking about the Richter scale, because then that allows us to talk about earthquakes and compare them to one another, so that instead of just saying, oh, there's a big earthquake and then a bigger one over there, we can say there was a 7.5 and then a 9.2 over there. And that puts things into context. It's kind of not a great analogy, but the idea is that we can assign labels, generalized labels to our code. So instead of saying something like great or or awful for our code, we can have a numeric representation of the performance of code. So that's what Big O is going to give us. Rather than colors and text like great, it's going to look a little bit different. It might look a little mathy, but it's actually pretty straightforward once you get past the first hurdle of it looking very foreign and weird. So one last point I want to make, some of you might be wondering, if I asked you to write a function that reverses a string and you get it to work, doesn't it only matter that you get it to work? Like, why does it matter what's best? The solution you come up with is the best. And in some ways, I think that depending on your project and the context, that's true. The best solution is the one that you can get to work. But when we're talking about things like interviewing, technical interview, code challenges, or working at a large company where you're working with a huge data set, let's say hundreds of millions of pieces of data, where one algorithm implementation could save an hour every time it runs compared to another implementation. Performance matters at that point, and there is an actual best algorithm or best solution. So it's important to have a precise vocabulary to talk about how our code performs. So even if you're content with your solution to something, it's helpful to be able to understand how it compares, how it performs compared to others. It's also good for discussing trade-offs between different approaches, because often it's not as cut and dry as I made it seem. It's not that one solution is always great and the other one is always terrible. Sometimes one solution might be great at handling really large data sets, pieces of data. Another one might always be very consistent in the time that it takes, but it might take more time up front. There's trade-offs, so it's not always just this is the best. Also, if you're trying to debug your code, it helps to understand things that are slowing it down. Not just looking for errors, but let's say that your code is working, but for some reason it's taking a lot longer than you expect, or your computer is lagging and freaking out in the browser when you execute some function. It helps if you understand some of the things we're going to talk about in this section in Big O notation. You can actually pinpoint where some problems might arise. So it helps us identify inefficient points. And then finally, you should care because it comes up in interviews a lot. A lot of times an interviewer will say something like, tell me the big O of this algorithm or of this function that you've written, or here's 3 functions, what's the big O? That will make sense in a bit, but it's important just to know for interviews. I said it's less important because hopefully you're learning it to actually understand things and to help you understand your code better and talk about your code better rather than just directly trying to master it for an interview. But interviews are important, so no judgment there either. So I'm going to leave this video off here. I'm trying to keep things more compact. Don't want any rambling videos. In the next video, we're going to pick up with a real example, some code, and start to analyze how efficient it is.